Contest for homework 2 at some point?
No.
Never?
We will think about it, but definitely not today. Okay, so let's start. Can you hear me there at the back? Okay, so welcome back. So I want to start by, in fact, before I get to it, two things. So one is there's going to be a new problem set available tonight. So you got a vacation. So we are past the halftime. There are going to be 3 more, and probably most of them, perhaps all but one, will be theoretical. So best case or worst case, depending on how you look at it, there's going to be one more programming assignment. Yeah. Oh, so someone said there that it is working. You're not. What about that corner? Not so good? Okay, it says that it's working. Let's try another one. How about this? Better? Yes? Okay. Okay, so anyhow, so as I said, one problem set will be, number 5 will be available. And will be due next Thursday. We are also going to make available a short exercise. Basically, the goal is stuff that I'm going to speak about. I think it's also not, yeah, I feel it. I don't know what's. That it's good. see volume, but it seems like it's working. So maybe it just needed a rest. So, okay, we'll try again. No? I don't think I have a volume. It says that it's full. So, I don't know. Let's try. Tell me if you can't hear me. Anyhow, so exercise and problem set, that's what I said. And I want to, and you did an exam, you probably remember, on Thursday. So the TAs worked very hard, and we have the statistics for the exam. So the grades are going to be released to Compass later this afternoon. Don't look for it now. And the exams are going to be available later this afternoon in my assistant's office. So 2 doors down for my office, or 3 doors down. You'll find it if you want to see it. So, okay. So basically, the average is 66, and the range is large. This is kind of the distribution, which is pretty nice. So 40 students got, what is it, greater than 80. If you want to see a little bit more of a split, so as I expected, there's a big gap between graduate and undergraduate. Why is it funny? I mean, I think that's not surprising, given the demographic of the class. Maybe I expected a little bit smaller gap, but that's kind of expected. And if you want to see split based on the questions, actually all of them are pretty much the same. Anyhow, you can just look at it, and so anyhow, I think, if people got more than 80 in the exam, you're doing, excellent. If you got less than that, depending on how much less, you should try to do better. But basically, I'm pretty happy with this spread and the result. So many of you did a really good job. Lost here and there, but really did a good job. Questions? No questions. Okay. So, okay, and thanks also for the surveys that you completed already a week ago, or something like that. So that's also helpful for us to figure out where things are. Okay, so I want to remind you where we were. So we talked about multi-class classification, and I want to talk about, complete this today, and put it in a slightly broader context of things that we've done, and then we're going to move from next time to probabilistic learning. So we talked about the composition, essentially. So the way we thought about multi-class classification was, here is a problem of categorizing into K things, and we're going to do it by decomposing into a binary classifier. And we did the decomposition in 3 ways. We did 1 versus all, we did all versus all, and we did error-correcting code decomposition. In all cases, the important thing is to realize is that actually what we optimized is each component separately. Right? So we kind of learned locally, and the idea was that the local learner doesn't know, in principle, about the other components. So even though our goal eventually is global, we learned locally. And each time we did it with a different decomposition. So that's an important thing to realize, and this is in fact an issue that we're going to discuss at length today, and is really important in other areas in learning. So, so really, the bottom line is that we don't really care about the performance of the local classifiers, but in this decomposition learning paradigm, we're going to optimize local learning algorithms and then use them to do something that is global. We noticed that also the decompositions sometimes are not guaranteed to be good, right? So this is especially true for the error-correcting output codes, where we kind of generated artificial decompositions based on the code that we've generated, and it's not necessarily that this decomposition can even be learned in a good way. So, and we talked a little bit also about the issue of efficiency in terms of how many classifiers we learn and how many examples we get from each one of them. So that's kind of a quick summary of what we did last time. And another issue is that all these approaches are not going to work so well when you have very, very large number of outputs. And this is something that we may want to think about. So I'm actually going to skip a few slides here that discuss this issue. Maybe I'll come back to them just because I want to focus more on the rest, and I think that, and I definitely want to finish it today. I'm not sure if I'll have time. So let's just recap what we did last time in a slightly different way. So when we talked about one versus all, we said, okay, let's assume we have k labels, n input features, and notice that we learned n times k weights, right? So we learned k classifiers. Each one of them had n weights. The training that we did was each set of n weights was learned separately. Each set of n weights corresponding to the ith label was learned separately, independently, just based on its performance on example X. That's how we decided whether we're going to update the weights if we're using Perceptron or do something else if we're using a different algorithm. So we didn't care about the performance on the same example by other labels, by other classifiers. Only at the end, the final decisions is global because it takes into account all the learners and does winner take all. So I like to think about this as the architecture. So these are all the features that we have. These are the k target nodes that we have, k labels. And each one of them is linked to the n, linked or may not linked if maybe one of the features is never active for one of the examples that belong to a specific target. But basically, we learn each sub-network like this separately, and then at the end, we do some global decision on all of them. Okay? Now, recall, so this is what we've done last time. Remember that we extended one of the algorithms that we talked about, we know, in a what then may not, maybe you didn't think about it as a very interesting way, but hopefully today you'll see that it is interesting. We introduced we know as an algorithm that learns monotone Boolean functions. It had very nice property, but it only learned monotone functions. So it started with positive weights, and it multiplies or divides the weights, which means all the weights remain positive. And that's not expressive enough, because we want to learn general linear function, not only those with positive weights. We extended it, and one of the key ways that we expanded it was this balanced we know idea, where basically we said, what we're going to do is we're going to keep two weights per variables, and the decision is going to be done using the effective weights, which is the difference between W plus and W minus. In fact, if you think about it, this is, in terms of decision, it's exactly the same as winner take all for the case of two. Right? You learn one subnetwork here for the positive, another subnetwork for the negative, and then you do winner take all on them. But the learning was different. The learning was not independently done for this left network and this right network. The net learning was done this way. we basically said if this dot product, the effective weight dot product with X, is greater than something, then promote W plus and demote W minus. So basically, we learn the two weight vectors together. And this is different than the standard one versus all. Of course, this is the binary case, but you can see that it's different than the one versus all in case of two. So the question is, can this be generalized to the case of K labels? And of course, there's the question of why should we generalize it? Why? So why should we try to generalize it to the case of K? What's wrong with one versus all? Yeah? What do you mean dependencies? We know that they are disjoint. So that's a dependency that we respect also when we do winner take all. At the end, we say only one is going to be on. Only one of the labels, so give me the maximum one, and that's going to be the label. So that's clearly there are dependencies from this perspective. But why should we care about it in the learning process? Yeah? Okay, so that's another issue that we brought up in one versus all, that the way we split the data is such that 1 over k of the examples, let's assume that if every label takes the same number of examples, then 1 over k of the examples become positive to one of the labels, and the rest, k minus 1 over k, become negative for it. So it's imbalanced. So that's an issue, but again, it's an issue that has to do with one building block. What I'm looking for is this. When one versus all is in the one versus all algorithm, we cannot deal with this case. We can deal only with the case where each label is linearly separable from the union of all the others. Right? Because we assume that we can learn the following situation where black is positive and all the rest are negative, which, by the way, can be done here. But we can also assume that we can learn with red as positive and all the rest as negative. Okay? And that cannot be done in this example. Now, last time, there were some questions that later on I figured out. So people suggested, why don't you boosting or something like this? And only later, when someone came to my office and asked the same question again, I think that I figured out what was the confusion. Anyone cares to ask this question again? Yeah? Okay, so here is the answer for this. So the game where boosting is a linear learner on top of the space of weak learners, right? So fix the space of weak learners. This could be just the features, the original features that you have. This could be small decision trees over these, or whatever you care to keep as weak learners. Over this space of weak learners, boosting is learning a linear function. Is that clear? So when I say linear here, I mean linear over some space. It's always the case that you can increase your expressivity by moving to another more expressive space, by building some functions over your linear space. So when I say this is not linearly separable, and you tell me, okay, so increase your expressivity so that now you will not be restricted by the fact, constrained by the fact that it's linear, I already did it, right? Imagine that I already did whatever we can do, and now I have a fixed feature space. I'm linear over this feature space. I don't want to increase expressivity further, right? Because you can always give this as an answer, but you know from what you know about learning theory that you don't want to do this too much, because you will just deal with a space of functions that is way too expressive for us to deal with, either because mostly because you don't have enough data to deal with two expressive function space, right? So we fix the function space, we fix the feature space, and as a function of it, we are linear over this. So the solution of increase the expressivity of your features is no longer a legitimate solution. Is this answering the constraint, the question? Basically, what I'm saying, the game we are playing now is we are using linear functions over some space of features. And I've already done everything I can do in order to increase the expressivity. I'm working over, a space of weak learners, if you want. But now I'm learning with linear functions. Okay, so it's not going to be, again, in the context of what we are doing today, a legitimate issue to tell me if you are concerned about linear separability, increase your expressivity. I already did this. Okay? Every time you do this, you'll run into the same issue. I mean, what about the linear separability in the new feature space? So that's where I am now. Okay? So now, in this new space, I can tell you 1 versus all is not good enough because of this picture. Because 1 versus all assumes that each color is linearly separable from the union of the others. And the question is, if we generalize this, will we be able to solve this problem? And the answer is going to be yes. It's clear, or it seems clear at least, or intuitively, that in order to address this, which I call the Voronoi diagram problem, we need some global approach. We cannot deal with local approaches that deal with each color separately, each label separately. Okay, so now I'm going to try to develop a global learning approach that is called constraint classification. As it will turn out, this approach has several interesting properties. Not the least is the fact that it actually leads very significantly into what is called structured prediction. Essentially, what we are doing here is structured prediction only expressed in a simple way. Now, most of you don't know and maybe don't care about structured prediction, but once you do care about this, and I'll give some hints at the end of this lecture, you will see the connection. But from our perspective now, we're thinking about it as a multi-class classification thing. So, okay, so here is the game we're playing, right? So we have examples. We have a black box learner that we don't care what it is now. And notice that before, we always thought about this black box learner as a function of x. But really, if you think about it, it's also a function of y, the label. Why is it a function of y also? Because when we did this decomposition, y told us how to do the decomposition. Right? It basically told us, you know what, split it to k classifiers in this way. Take the examples that are labeled 1 and make them positive here, negative here. Take the example labeled 7, make them positive here, negative here. So the y was actually used also as part of the learning protocol, right? So this is really what we've done. We said there is some function that depends on y of x, and it's this. And we make decision using wi transpose dot product with x. And then the prediction itself is the argmax of this. So try all y's, evaluate fy of x, and choose the y star. That's what we did. This is the 1 versus all. Now, here I did not tell you yet how I learn. I just told you if you have this w, y, this vector, then this is how you're going to make decisions. Equivalently, we could say that we predict in the following way. We predict y if and only if for all y prime that is different than y, wy minus wi prime dot product with x is positive. right? So basically, that means W1, Wy beats all the Wy prime, right? It basically says Wi dot product with x is greater than Wy prime dot product with x for all y prime, which makes him the argmax. It's clear that this is the same. And again, as I said, we didn't say how we learned these k-weight vectors, but only talked about the decisions. Now, notice that at the end, what we do is we learn one k n-dimensional weight vector, which is the concatenation of k vectors, each one of dimensionality n. So now I'm going to introduce a construction. It's called Kesler constructions, even though it was rediscovered. So this is, again, a kind of an interesting story about how science progresses. So actually, Dav Zimak, one of my students about 10 years ago, discovered this construction. It was very nice. And then it turned out, after the first paper on this was published, not because any of the reviewers knew about it, no one knew about it. Actually, one of my other students found out in some esoteric place that this was actually discovered about 30 years ago by a physicist that was doing something. But anyhow, so it's still called Kesler constructions, and here is what it's doing. So we're going to represent each example xy as an nk dimensional vector, and I'm going to denote this nk dimensional vector xy because it's going to start with x, but will depend on the label y. And this is what's going to be. It's going to be an x embedded in the yth part of an nk dimensional vector where all the rest are zeros. So I'm going to think about this as an nk dimensional vector. The kth component of it, or the yth component of it, is going to be, I'm going to place x there, and all the rest is going to be 0. Okay, so in this case, I have k equal 4, and y is 2, so it's the second part. And I don't care what n is here. So each one, this 0 is really an n-dimensional 0, and this x is also an n-dimensional x. Okay? The notation is clear? So now, if we by this notation, what I said before about the decision, predict y if and only if, for every y prime between 1 and k, this decision, wi minus wi prime dot product with x is positive, can be written also in the nk dimensional space in this way. W is now the nk dimensional vector. xy is this nk dimensional vector. xy prime is also an nk dimensional vector that is all zeros except for the y prime component. And I'm saying that this is equivalent to this. So think about it. I have an nk dimensional vector where everything is 0 except for the y component. Another nk dimensional vector where everything is 0 except for the y prime component. So really, what I get from this dot product is just wi dot product with x, and from this component, it's just wi prime dot product with x. And I'm denoting this, this is still the w, and I'm denoting this difference between xy and xy prime as xyy prime. So xyy prime is an nk dimensional vector. One component, the yth one, I placed x in it. In the y prime component, I'm placed minus x. And the rest is 0. Okay? So this is the key construction. And there's a lot of notation. I'm going to show it again later with some graphics, but this is the key construction that we have to understand. What does this give us? It gives us essentially a mapping between examples that were in the n-dimensional space to examples that are now in the nk-dimensional space. So I blew up the feature space significantly. And I defined two sets of examples. The examples x, y, y prime, they are positive because I'm requiring that if W is the separating vector, you can see that x, y, y prime is positive. Yeah? No, it's just a vector. So what I did is I did two things. First of all, I concatenated all the vectors, all the WIs that you somehow learned. I don't care now how you learned it. And I have an nk dimensional vector. Now I'm generating from the x, the examples, also an nk dimensional vector. How do I do it? I take x, I generate an nk dimensional vector and I'm placing x in the y-th component of it. So it has k components for label 1, for label 2, for label 3, for label k. In the y-th place, I'm placing x, and I'm calling this x subscript y. In the y prime place, I placed x again, and I call it xy prime. And I do this for every y that ranges from 1 to k. So now, if this w is a good w, then x, y, y prime is positive. So basically, I'm defining a set of examples. X, y, y prime are all positive examples. And the negative of x, y, y prime are all negative examples. Right? Look at this here. This basically says x, y, y prime is positive for w, and consequently, minus x, y, y prime is negative. Okay? So these set of examples are linearly separable. So bear with me one more slide. In fact, let's get it now. Yeah. Okay, excellent. So how large is this set? Let's look at it here. So given a data set of m examples with n-dimensional x's and k options for y, I'm creating a binary classification task in the following way. I'm generating a set of positive example, xy minus xy prime, a set of negative example, xy prime minus xy, and I'm doing it for every y prime that is not y. So how many do I get? I get, for every example, I get k minus 1 positive example and k minus 1 negative examples. So altogether, from m examples, I got 2 mk minus 1 examples. Okay? So that's a good sanity check for us to figure out that we understand what's happening. Now, again, I didn't say how we learn it. All I said, I took a multi-class classification problem and I embedded it in an nk-dimensional space, and what I got is that now I have a linearly separable collection. And you can use your favorite linear learning algorithm to train this. My prediction is essentially just like I did before. Given an nk-dimensional weight vector W, which is what I got, I'm going to do argmax over all possible y's of this new dot product, the nk-dimensional dot product, W dot product with xy. Okay? So let's do this again now with more colors, and I think it will be clear. So I'm starting with this set of examples. 4 colors, blue, red, green, and yellow. And really, what do I know about this blue, which is not my number 2 label? I know that if you give me an example that is blue, like this one, I know that the weight vector that I learn has to satisfy that 2 is going to bit 1, bit 3, and bit 4 on this example, right? W dot product with this example is going to be larger than the same thing for the red, the same thing for the yellow, the same thing for the green. Now, what I'm doing is I'm blowing up this example. Each example in the blown up space already corresponds to this pair of examples. So essentially, I have an example here that corresponds to the fact that 2 is bits 1. So I took X, I embedded it in the nk-dimensional space together with not X in the 1 position. And then I did the same thing with not X in the 3 position. And I did the same thing with not X in the 4 position. So each of these examples, which has nk dimensions, but only 2n non-zero. Each one of these examples corresponds to 2 beating another label. Right? It's the y prime, where y in all cases is 2, and y prime is 1, 4, and 3. So this is really what I did. I generated my xi. I generated my xj. And xij is just the difference between them, so it looks like this. And I'm working, okay, so to confuse the enemies, now instead of n, I put d here. Just notice that. But I'm sure you can handle it. It will just make sure that you're following. So this is what I got, right? So if I have a function, fi, that beats fj, which means wi dot product x beats wj dot product x, that means that in the n-dimensional, nk-dimensional space, I also have this, where now this is the big vector, and this one is this guy, the embedded of x in the nk dimension. This is the embedded of xj, and this is what I called xij. Okay, so this is basically the details of this construction. This is just saying something that I already said before, that I'm starting with xi, right? So someone told me x is labeled I. So I'm generating k minus 1 examples, xij, as positive example, and the negative of them are the negative examples. Okay, so with more colors, I want to predict y, which is going to be the argmax over red, blue, green, y of this dot product. So essentially, I need to find these 4 weight vectors such that for this specific x that I know is, what color did it? Blue. No, sorry, red. Red is the winner here. W red beats WB for this x. It beats W green, and it beats WY for this example, because it's a red example. Okay. So I'm just concatenating this. If 0n is the n-dimensional 0 vector, essentially what I'm doing is I'm rewriting this way. Right? So I have x in the red spot, I have b, I have minus x in the blue spot, and the rest are zeros. And each component here is really an n-dimensional thing. And I'm doing this for the green, and I'm doing this for the yellow, and this essentially says this example x is a red example. Right? It beats all the other colors. So, and these are all my positive examples, and just the negation of them are all negative examples. So basically what I've shown is that there is, if this is satisfied, which is what we are after, so notice that this is kind of a local thing, right? Basically I'm saying, if you can find a W that separates the red from the green, separates the red from the blue, separates the red from the yellow, then in the nk-dimensional space, there is a global weight vector that separates everything, does everything as we want. So in the nk-dimensional space, we have a linearly separable thing, which is kind of magic, I think. So this is, again, just another way of saying what we are doing here. So the construction of the examples, this construction of this P plus and P minus, and notice that P plus of xy has k minus 1 examples, P minus also has k minus 1, right? So for every example, I'm generating k minus 1 examples now. Okay, so now that we understand the construction, we can learn. And in fact, we can learn with any algorithm we want that we know learn linear separators. So we're going to find this W that separates P plus from P minus. You can use Wino, Perceptron, SVM, whatever you want. The important thing is that this is what we're going to get, right? We're going to get that this big W dot product with x, y, y prime is positive, which is equivalent to, now I'm writing it slightly different. Before I wrote it as W with xy minus xy prime, but it's exactly the same. I can write it also as wy minus wy prime dot product x, right? Notice that it's exactly the same thing. Here you have a big W. Here you have a big X, but only two components of it are non-zero. All the rest is zero. So these components correspond to the Wi and the Wi prime. Right? So this is exactly the same as this. Once you understand this, you're done. And you should notice that this is exactly what we've done in the balanced Wino. I'm going to come back to it a little bit later. But first, let's develop an algorithm. Even though I said we can take any algorithm, let's think about what would Perceptron do in this specific case. So Perceptron says, okay, I want Wt dot product with xij to be positive, or equivalently this, which means that if I make a mistake, given this example, xi, x is labeled I, for all ij, where j is different than I, right, so all the other labels, I want to make sure that I beat them. That is, if I see this, if I see the wi minus wj dot product x is negative, it means that I made a mistake, right? I need to update. What does it mean to update? In the Perceptron case, essentially, you can think about it directly from this case, right? What you're going to do is you're going to promote this W. You're going to promote this W only in the non-zero components. Promoting this W essentially means promoting Wi, but demoting Wj because we have minus Wj there. So again, I'm running the simple Perceptron in the nk dimensional space, and I'm translating it to you back to the n-dimensional space. What I'm doing really is promoting one, the correct one, the I, and demoting the j for all j's that are wrong. And this is exactly the balanced Wino update rule. Yeah. Okay, very good. So I'm running Perceptron, which means that I'm promoting for every example that I have. Now, for each original example, now I have k minus 1 examples. The example was labeled I. Now I have k minus 1 examples in the new space corresponding to all those indices that are not, all those labels that are not I. So basically, when I promote the ith, I'm going to demote all those j that are bad here. Could be k minus 1 demotion. Right? No. So I'm promoting one. I'm promoting wi. Okay, so I will do this. Okay, so yes, I will do this k minus 1 times. Right? So everything I'm saying here, I'm saying it for all ij. So this is one case. For I equal 1, j equal 2. Now I'm going to do the same for I equal 1, j equal 3, and so on. And k minus 1 demotions for potentially all the other j's. Yeah. I'll get to this point in a second again. But this is what comes out directly from applying the perceptron on the nk-dimensional space, right? So this is clear? Okay, so we promote wi, and we demote all the wj's that are for j that are not I. That's what happens here. So two issues. One is really this is a generalization of the winner rule, which is nice. Yeah. I don't have to. No. I can actually go back to the picture that I showed before, and I think I'm going to show again, of this network of k subnetworks. And I'm going to work in each one of them separately. The only issue is that when I do the update, I'm doing the update globally. I'm not only updating each subnetwork separately. So this is really just a conceptual way to think about it. I don't need to implement it this way. In fact, I will implement it very similar to the way we implement Perceptron, only that I'm going to keep track on who's winning here and who's beating who. And as a function of that, here, J was beating I, and therefore I'm going to demote J and promote I. Yeah. Say it again. In the inner loop, I have fixed I, and I'm changing J. But I'm going to do it really for all I and J. Yeah. Yeah. So for each wij, I can do this. Now, in practice, and this is the next slide, so this is the right way to work. In practice, what we are typically doing is, and this is, by the way, what all the theorems that I'm going to quote apply to. In practice, we are running a more conservative update. While the general scheme says that, given an example xi, I'm going to check this condition, and I know that I should beat all the j's. And I see here that I found a j that beats I, and therefore I'm going to promote I and demote j. In practice, we are just going to do a conservative update. And this is the implementation that we actually have in Snow in LBJ. And basically what we're going to do is we're going to choose the worst j, or the best j, depending on how you want to look at it, and demote only the ways that correspond to the target node that correspond to this j. So essentially what I'm going to do is I'm going to look at wj.productx. Right? I know the wi.productx has to be the highest. Right? I'm looking at the argmax over all j, wjx. And if this guy was mistaken, beats I, I'm demoting it. So I'm not going to care about all the other j's in this case. I'm just doing it once for the top one. And, this is going to save me time. And it's more conservative. And this is really how we're going to do it. So in this case, I'm, again, just doing the promotion for I and the demotion for this J star, which is the closest J, or the worst J, if you want. Yeah? In fact, I don't know how to prove, at least not off the top of my head, that this conservative version converges. But in practice, this is what people are using. instead of the correct one, and it turns out to perform about the same. But good question. Yeah, I don't have a good answer beyond the fact that it's a simpler version, simple heuristics over the correct algorithm, and I don't know how to prove it. Yeah. I'm only correcting if it made a mistake. No, but WJ was, so basically think about it this way. We have a linear separator, right? So essentially what I'm saying, think about, you have several candidates. Some of them are far away from the line, and one of them is very close to the line. I'm actually correcting my line based on the one that is closest. Basically, this is what it says. Right? Yeah, but if you think about, let's see, do I have any? Okay, if you think about the Verona diagram, you could think about it a little bit as correcting this part of the line. So I'm changing this part of the line only, and I'm changing it based on the example that is closest to it, rather than those examples that are farther away. So I'm not going to be influenced and change it again and again because I have some other points. I'm just changing it based on the one that is really the key competitor. That's the intuition here, and that's why I think it works, although I'm not sure that it's easy to prove in the conservative case. But the intuition is that rather than changing something globally, of course, this is not the right picture because everything should be observed embedded in an k-dimensional space. But the intuition is that I'm changing just part of the separator. But I'm changing the right part of the separator because I'm dealing with those examples, or this example that bothers the ith label the most. That's kind of the intuition. Okay, so let's, anyhow, so hopefully, again, you don't have to do it this way. You can just do k-1 updates or up to k-1 updates. All I'm saying is that in some sense, you could view these other updates as a waste because they were easier examples. They were easy. And they should be fixed if you fixed it for J star. So let's go on, and you'll ask other examples later. So, okay, so this is the, basically I'm not changing the other components of the weight vector. Okay, so I want to give one more example of how this is being used, but before that, let's just stop and think. So what have we done? So basically, we learn a hypothesis that is more expressive than the one versus all, right? Because we can actually solve the Verona diagram example. We actually show that if there is a linear separator between each pair of two colors, then in the nk-dimensional space, there is actually, the problem is actually linearly separable. That's what we exploited. We can use any linear learning algorithms. In fact, we can use support vector machines. And I'll show this in a minute. One important issue that comes out from this is a natural notion of what is a margin. So if you think about it, we have a clear notion of a margin in the linearly separable case, right? In the binary case. What is the right notion of a margin in the multi-class classification? We also want to have a margin. So by this embedding, we actually get a natural notion of a margin because we're going to embed it in the nk-dimensional space, understand what margin means there, and then translate it back to a notion of a margin in the multi-class classification. What do we get? In the nk-dimensional space, given an example xij, the margin is the minimum on all pairs, ij, of this dot product in the nk dimensional space, wt xij. This is the standard notion of margin for each example. If you break it down to the Rn space, what you get is you fix I, right? So given an example that has label I, the margin of X is the minimum over all J of the difference, Wi minus Wj dot product X. So essentially, find the W, the J, that bothers me the most. Let's look at it. Okay, where is it? Okay, in pictures. This is the natural notion that we have, where we have examples, positive example, negative examples, and we look at this example that is the closest to the hyperplane, or if you want, closest to the negative examples. And if I want to generalize it to the multiclass classification, really what I'm going to do is I'm going to look at W subscript label dot product X. The right one is the blue one here. And I'm going to look at all the values and choose the one that bothers me the most, that is closest to me, and say that the gap between them is my multiclass class margin, right? This is the notion that came out naturally from our embedding, right? So again, this is the notion that we got. Look at the W, the J, such that Wjx is the closest to Wi. This, in fact, gives us an algorithm. This came out of order somehow, so we'll go back to it. It gives us also an SVM algorithm. So in the same way that I gave you a Perceptron algorithm that perhaps is easier to understand, you can also think about an SVM. So typically, the hard SVM is this, right? So we're minimizing W square, subject to the fact that all the examples are satisfying this, right? So all the examples are y times dot product x is greater than 1. In the multiclass, I'm replacing it by minimizing the same thing, such that Wi beats Wk for all the examples that are labeled I, which is exactly the same thing that I did for Perceptron, right? So again, this embedding naturally gives me also an SVM. Again, historically, it's kind of interesting because people have suggested this algorithm at about the same time, within half a year, from the suggestion of the Perceptron algorithm, only that in the SVM case, it was just suggested kind of in an ad hoc way, based on intuition, good intuition, as you can see. In the Perceptron case, it was suggested based on this Kesler construction case, and it turns out that it's the same thing, which gives some, satisfaction. And the same thing, by the way, you can say in the general case, right? So the only difference is that here we will have the soft case, we will also have this component of the Xi, but still, the key thing is that what we are requiring is that if the example is labeled I, then Wi is going to beat Wk for all k that are different than I. That's basically it. Okay, so questions on this? I can go back to 37, which was supposed to be after it. This is some kind of a summary. So basically, we presented the scheme that gives a uniform view. I didn't actually show why it gives a uniform view, but I'm going to show it. The reason, by the way, it's called constraint classification because everything can be viewed as representing labels as a set of constraints or preference among the output labels. What do I mean when I say this? Let's think about some other problems. So we talked about multiclass. What is multiclass? You can think about as an example. You can think about the set of labels as a set of constraints over the labels. What I want from example X is that A will beat B, beat C, and beat D. This is what multiclass means. Every time I have one label that beats all the other. With the same notation, I can say, you know what? I can also have a multi-label setting where the label is AB, where by that I mean that there is a partial order. A beats everyone else but B, B beats everyone else but A, and there's no order between A and B. Right? So A beats C and D, B beats C and D. I can also think about ranking the labels. Right? I could also say, I want to label X with a permutation over the labels. And this is what the permutation means. It means that 5 beats 4, beats 3, and so on. If you think a little bit about it, the general setting is that my label now is not a number, but rather a permutation over the labels. And I'm defining some preference as a way to define the problem. One type of preferences defines multiclass, another type of preferences define multi-label, another type of preference define label ranking. And this is what I'm going to learn. The nice thing here is that the same algorithm that I described before, in fact, is going to work. So if you think about it, just like in the multiclass case, I'm going to learn one WI for each label. I'm going to concatenate them together to live in the R, in the NK dimensional space. But if you think about the algorithm that I described before, you will see that the same algorithm is going to work here too. So what did I want here? Here I wanted WI to beat WJ for all J. Right? For all J, I want to do this, or if I see this, if I want to do multi-label, basically that means that if A and B are the labels, I'm going to make sure that A and B beat all the others, and I don't care about the order between A and B. Everything else stays the same, right? I immediately have an algorithm. If you want to do ranking, you can do the same thing. You want a specific ranking for this example X. So you'll make sure that all the order constraints are satisfied. If you want 1 to be greater than 2, greater than 3 for this example X, you will check W1 against W2 for X. If the order is the way you want it, do nothing. If the order is not, promote and demote accordingly. Then you check 2 against 3 and do the same thing. So each one of the algorithms, essentially, each one of the formulations works in exactly the same way. The only thing you will change is you will change when this is going to cause a mistake. So this is the nice thing about this formulation, that you can really do all these settings, multi-class, multi-label ranking, with the same formulation. Okay. Okay. So there are some properties of these constructions that I kind of talked about, and as I said, at about the same time, people suggested an SVM algorithm that is essentially the SVM that I showed a couple of slides ago, which is the same algorithm that we proposed for the perceptron. The difference there was that the notion of margin wasn't justified. It was kind of an intuitive notion of margin, but it wasn't justified, as opposed to when you look at it in the NK dimensional space, you clearly see what a margin is, and then when you break it down back to the n-dimensional space, you get what you want. So, but anyhow, all these algorithms, so it was suggested in the context of SVM, it was suggested in the context of Winnow. Basically, people took the balanced version of Winnow and generalized it to the K label case. And then constraint classification was suggested all at about the same time and completely independently. Again, this is the picture that you can imagine for the multi-class classification, although I'm not sure if this is a convincing picture. It's not as intuitive as this picture. OK, so one can prove some bounds, and I'm not going to get into the bounds. Basically, one can show that the algorithm is doing the right thing. You can prove some generalization bounds. And the one thing that I want to talk about is performance. So hopefully I convince you that this is the right thing to do, right? So this is the right way to do multi-class classification as opposed to one versus all. Nevertheless, if you do experiments, you will see that in low-dimensional cases, if the problems are hard enough, of course, if things are easy, you don't need to do the right thing. But if the problems are hard enough, you will get into these Verona diagram situations, and therefore, constraint classification is going to do better than one versus all. It turns out that in very high-dimensional cases, it's not that important. And the reason is, or at least my interpretation of it, but maybe there are some still things to understand there, is that everything is anyhow linearly separable. So every label is anyhow linearly separable from the union of the others, or almost linearly separable from the union of the other, so you don't get a lot of advantages from not doing one versus all. But anyhow, this is one thing that is good to realize, and I think it has implication also on other harder problems in the context of structured learning, and I want to say a little bit about it now. So, okay, so we talked a little bit about a few other problems, ranking, multi-label. One of the key interesting extensions of this is when you have huge amounts of classes. Not only 10 classes or 20 classes or even 100 classes, but rather millions of class labels. And this case comes up when you have a structure that you want to label. Think about a sentence. If you want to label a sentence with part-of-speech tags, so in English, for example, the standard labels for part-of-speech tags are 45 different labels. Versions of nouns, adjectives, verbs, prepositions, and so on. 45 different labels. If you have a sentence of size 20, that means that you have a lot of sequences of part-of-speech tags, right? In each place, you can put 45 things, so it's 45 to the 20 potential sequences. Of course, most of them you will never see, but you could see a huge number of labels. So if you want to try to use this as your label space, it's a multi-class classification that is way too large to handle with standard multi-class classification. So, and this is what we call structured prediction, where we have a huge label space. But of course, these label spaces are not independent. For example, I know that it's very unlikely that I will get in these labels 2 consecutive verbs, right? If you think about it. So the label space is somewhat constrained in different ways, but it's still huge. So this is what we call structured prediction, and this is actually what we cover typically in CS 546, although this year we will not teach 546, so you'll have to wait for next year. But here are some examples. Sequential predictions, or in general, structured output, parse trees, or many other things. So the nice thing about the structure, the constraint classification approach that I showed is that it's essentially structured prediction. So the same formulation that I described today goes essentially almost directly to the formulation of structured prediction. I want to give an example, though. So here is an example from another structure classification problem that is called semantic labeling. The idea here is, given a sentence, I want to be able to chunk it to pieces. Each color here is a piece. I'm doing it relative to the verb, so the verb is live here. And I want to know that I and deliver. And my Perl is the things left. To my daughter-in-law is benefactor, and this is some kind, in my will is some kind of location arguments. The names in the specific formulation is A0, A1, A2, and something else. But really, you can think about it really as a chunking problem, where you take the sentence, you identify where to chunk it, and then you color each one of the chunks with a different color. One color is called A0, another one is called A1, another one is called A2. So the issue is that, of course, there are many, many ways to do this. Some of them are illegitimate in the sense that you have overlapping chunks. Some of them are illegitimate for different other reasons, right? So maybe you have a set of constraints on what is a legitimate output, just like what I said for parallel speech tagging, where you don't allow two consecutive verbs. So basically, you want to be able to eliminate a lot of them and remain with one. One of the interesting things is that the same consideration that we had in multi-class classification appears here. So we started this lecture by saying what we've done before with one versus all is we learn local classifier. Each classifier learns by itself the label 1, the label 2, the label k, and doesn't know what the other components are doing. And only at the end, you make a global decision. You say, I want to take the winner take all. Right? So the same thing can happen here, right? So you can think about a global learning algorithm where I'm going to learn what is A0 separately without caring about what's A1 thinking and what's A2 thinking and so on. I'm going to learn a classifier for A1 without caring about the other classifiers. And at the end, I'm going to put them together into one chunk, one chunking of the whole sentence. So this is what I'm calling here the local, where each component learns separately, versus global, when I actually work in this huge dimensional space. So you could imagine that constraint classification is more similar to the global learning versus the local learning that learn each label separately. And even in the case of structured prediction, there is always the question of which should I do? Should I learn separately and only take the global consideration at the end, kind of like the winner take all, or should I learn everything together? And what we've done today, actually, as I said, is very similar to consideration that people think about in this case of structured prediction. Okay, that's all I wanted to say. And next time, as I said, we're going to start with probabilistic learning. Okay, so see you on Thursday. Hi.
I was wondering if you'd sign this for me. Just dropping out of 3 credits from 4.
You're dropping from?
4 to 3.
Okay. So you did not send me a...
Correct.
And what is today?
The 28th.
28th, okay. Okay.
Thanks, sir.
I had a question about the update rule.
Yeah.
It's for all IJ, but we know the label is I, right? So shouldn't it only be for the I that is the label?
Yeah. So that's the update rule. So let me just.
Okay.
Get it.
That was a little bit
So I have an inner loop. For a given I, if I know that this example is I, I'm running all the J.
Okay.
But I have to do it for all labels also.